Okay, this is 2018, number 1. And so if we read this, a student wants to determine the value of acceleration due to gravity for a specific location, sets up the following experiment. A solid sphere is held vertically a distance h above a pad and by an electromagnet as shown above. The experimental equipment is designed to release the sphere when the electromagnet is turned off. The sphere begins to fall. A timer starts when the electromagnet is turned off, and the timer stops when the sphere hits the pad. While taking the first data point, the student noticed that the electromagnet actually releases the sphere after the timer begins. Would the value of G calculated from this one measurement be greater than, less than, or equal to the actual value of G at the student's location? Okay, it would make, what happens is if the timer turns on before the sphere is let go, then that's going to make the time long. And so the time would be too big. And so if we look at, if we just do this equation, delta x is v naught t plus 1/2 at squared. I know I'm going to travel h, or negative h, however you want to call it. V naught is 0 because it's released from rest. So I get 1/2 gt squared. So if I solve for g, it's going to be 2h over t squared. If my time is too long, it will make this division, I will divide by a bigger number, and so therefore it will make g less than. So it's less than because of that. There's your justification. All right, in B, the electromagnet is replaced, so the timer begins when the sphere is released. The student varies the distance h, and they measure and record the time t for each particular height. So they release it from h, and they record how long it takes. Indicate below which quantity should be graphed to yield a straight line whose slope could be used to calculate for g. Well, I just did a calculation for g. I said g would be 2h over t squared. So what I would plot on the vertical axis would be 2h, and what I would plot on the horizontal would be t squared, because it would be rise over run, and that would be my slope. And then they tell me, they say, okay, well, you got this table. Go ahead and calculate those things that you want and put it in this table, including units. Now, this is the table that I'm talking about that they want us to put it in. So I'm going to create that table right here. And so this is going to be 2h in meters and t squared in seconds squared. And so we start with 0.1, so that'll be 0.2. 0.2, so that's 0.4. 0.6, so that's 1.2. 0.8, so that's 1.6. 1, so that'll be 2. And then as I square the bottoms, we've got 0.105 squared, which is 0.011. 0.213 squared, which is 0.045. 0.342 squared, which is 0.117. 0.401 squared, which is 0.16. And 0.451 squared, which is 0.203. So 0.203. Okay, so there's my values that I get. And then they want me to plot these and draw a best fit line that does this, goes through this. Now, I did actually print myself a grid this time. It's kind of a light grid. It didn't turn out very dark, but I'm going to go ahead and do this. It's the same grid that you have. And so I'm going to plot my vertical is going to be 2h in meters, and then this is going to be t squared in seconds squared. So look at my x. I go from 0 to 0.2, so 0.05, 0.1, 0.15, 0.2. That sounds good to me. Okay, now we're going up. 2h goes from 0 to 2, so how about 0.5, 1, 1.5, 2. All right, and so now let's plot these data points that I have. Let's see if I can get both of this on the screen. Okay, so remember this is my x and this is my y. So I'm going to go 0.011, so that's going to be about here, and 0.2, 0.045, and 0.4, 0.117 and 1.2, 0.16 and 1.6, and 0.203 and 2. So there is my plot, and now I'm going to put a best fit line through that data, and that data actually fits really, really well. So that looks nice. Okay, now, put our other thing back here. Using the straight line, calculate an experimental value for G. Okay, so I just said up here, according to what I said here, I said G is going to be the rise over the run. So on that, G is going to be my slope, because that's what I figured that it's going to be. So we just need to find the slope of this thing. So this is the answer for D. So I'm looking for the slope. So what I'm going to do is I'm going to pick some points where I get nice intersections with the grids, because that's what we're supposed to do. We're supposed to find places where this line crosses the intersection, and that point looks really good. Let's see, let's go down here. Let's say that point does. So this is the point 0.1 and 1, and this is the point 0.18 and 1.8. So I'm going to do those. So 1.8 minus 1 over 0.18 minus 0.1. And so that's going to be 0.8 over 0.08, which is 10. So that's our experimental value for G. Now we're going to do this, and it says another student fits the data to a quadratic equation. And they give us the values here, that y is at squared plus bt plus c, where a is this, b is this, and c is this. Vertically down is the positive direction. So I'm going to go plug all these things in. And so y is going to equal 5.75 t squared minus 0.524 t plus 0.080. So that is my equation for position. Using the student's equation above, do the following. I derive an expression for velocity. This is an exercise in calculus. So we say, well, I have a position. How am I going to find velocity? I'm going to take the derivative. So I'm going to do that. So I'm going to get 11.5 t minus 0.524. And that's going to be my expression for velocity. On 2, they want me to calculate the new experimental value for G. Well, wouldn't that be the acceleration? So let's just take the second derivative. So we'll just derive this, and we get 11.5. Now, if you go back and you recognize that this is v naught t plus 1/2 a t squared, this is 1/2 a, which is 11.5. Yeah. All right, 3. It says using 9.81, calculate the percent error between this value and the 9.81. Well, I'm going to take the 11.5. I'm going to subtract the 9.81. I'm going to divide by 9.81. Times 100. Actual minus theoretical over theoretical. What I got, what I should have got, divided by what I should have got. So I'm going to do that, and let's see what that gives me. 11.5 minus 9.81 divided by 9.81 and then times 100 gives me a 17.2% error. And then lastly, IV. It says, okay, assuming the sphere is at a height 1.4 at time 0, calculate the velocity just before it strikes the pad. So we're looking for the velocity when it strikes the pad. Well, let's see. What can we do to find that? Our h is going to be that. So let's just see. Well, I think we could just do this. V final squared is V naught squared plus 2a delta y. That's what I think I would do, because we don't have, we have constant acceleration. And so V final is what I'm going to look for. And so that's going to be 2 times my acceleration, which is 11.5, times that distance of 1.4. So 2 times 11.5 times 1.4, square root of that. And I get 5.7 meters per second.